Okay, off we go. Okay, so we've got a little over 15 minutes left. So here's where we were last time. Oh, I didn't turn this. Oh, I got to plug this thing back in. Sorry. There we go. Okay, now this is where we were last time. We were talking about this idea of intermediate variables. I hadn't really gotten to explaining what that is yet. But what we did is we looked at the matrix form of the chain rule. Right? This is what we justified the matrix form of the chain rule by arguing about how, roughly speaking, velocity vectors of the relevant inputs and outputs relate by derivatives, and you compose matrix multiplications, and it just kind of is what it is, right? It is a vector point of view, ultimately a very powerful and simple way to look at the chain rule. But it is very high level and sort of sophisticated. So when we write it all down in terms of coordinates, this is what you get. And in particular, we talked about how any given element of the derivative of the composition, derivative matrix of the composition, it's just a dot product. It's this dot that, which we write like so. And then we spent a little bit of time talking about the notation, this very unfortunate notation, but again, you really cannot view, for example, this as being a fraction. And I know we write it as a fraction, but it's not. In a given very specific context, you can set things up and define interpretations exactly appropriate to that one context and make sense out of it as a kind of a fraction. Absolutely. Right? But by itself, standalone, not a fraction. This thing here is just not the same as that thing there, and so it just doesn't make sense by itself. Okay, so with that warning done, let's ask, okay, well, how can we sort of make sense out of this equation? You don't want to have to think about it in terms of matrix multiplications every single time, right? So here's my proposal. I think this is a nice way to think about it. And this is where intermediate variables comes in. So think of this in relation to this diagram. Now, this is kind of just a reproduction of the diagram we have on the previous page. The first function gives the y variables as functions of the x variables, right? And then this part sort of represents how the z variables are functions of the y variables, and of course the composition is, going from those all the way sort of, over to those. Okay. All right. So the big idea here is that when something changes, and the presumption of saying I want to take the partial with respect to xj is that xj will be changing. Now, with the understanding that all of this remains constant and all of this remains constant. Yeah, sure. Right. Okay, but as xj changes, there's downstream consequences. In some sense, everything else is going to change too, because it all depends, ultimately, trace it all back, it all depends somewhat on xj, right? So, all right, so let's think about, I've got this arrow right here. What do I mean by that arrow? That's just representing the way in which y1 depends on xj. Now, of course, y1 depends on other things, but those other things are being held constant. So what do we know about this idea of how y1 changes when xj changes, with the understanding that all the other x's are held constant? Well, we have a name for that. That's the partial derivative. Specifically, it's this partial derivative right here. So that's the factor that says, okay, when xj changes, by what factor multiplied by that does y1 change? All right. Now here's the thing. That y1 changing wrong color. Sorry. The change in y1 will then cause ultimately a change in zi, the thing that we're ultimately interested in. Right? So we know that when xj changes, what I have in purple here represents by what factor will that change be sort of magnified to give us this change. Now, okay, well, yeah, but that y1 changing, now forget about everything else changing. Yeah, there's a lot of other things changing. But just the mere fact of y1 changing will cause zi to change, and there's a multiplicative factor there, right? What's the multiplicative factor relationship between y1 changes and zi changes? And we have a name for that as well. That is this partial derivative right there. So here's the big punchline. The big punchline, oh, I didn't want to erase that. The big punchline is that if you are interested in this partial derivative, orange with respect to green, overall, let's see, color choices. This path of propagation, right? Changes in xj will propagate along that path. And this term right here is the sort of altogether, sort of the combined, given both of the steps in this path, this is sort of the combined factor of how much do xj changes cause zi changes as propagated through the y1. All right, so we made the argument here for one term. This one term corresponds to this path. And here's the thing. There are other paths, right? There's a y2 path and a y3 path and a 4 or 5, it's a blah, 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 all the way down and including the ym path. And so each path correspondingly has a term. And there's that last one, the ym term. Okay, so what do you think so far? Right? Now, we're not proving anything here, right? This is just I like to think of this anyway, as a way to interpret this equation we already knew. We already established this by the matrix form of the chain rule. We already knew this was true. What we have here, then, is a way of thinking about it outside of the matrix context. Right? And so think of it as each one of these terms corresponds to a path, and then I make the modest observation that, well, yeah, okay, but every path corresponds to one of these intermediate variables. So, for example, let's look at the last one, just to mix it up. This path corresponds to the ym intermediate variable. And I call it an intermediate variable because, well, it's not one of the initial inputs, and it's not one of the eventual final outputs. It's kind of the one kind of in the middle, in the intermediate stage of the composition. Okay, so every term corresponds to a path, which corresponds to an intermediate variable. Okay, and for whatever it's worth, in practice, day in and day out, while you're sitting there chugging out partial derivatives, it's a really good way to think about it. It's very convenient, I guess I'll say. Now, I do feel it necessary to point out that ultimately, when we're talking about the chain rule itself, for sure, you should think about the chain rule this way. This, because of what we argued about, there's a matrix factor there and a matrix factor there, and altogether, factors multiply. This is overwhelmingly, in my opinion, the best way to think about the chain rule. Big picture, why does it work? I think this is hard to argue with, right? But again, in a sort of like a daily use, I don't really care about all the variables. I don't want to have to write down the whole derivative. Oh my God, the derivative matrix could be big. And if all you're interested in, let's see here, let me go back to, if all you're interested in, and this is often the case, if you just really only care about that one partial derivative, I don't need the whole matrix. And therefore, I only need just these partial derivatives. It's kind of nice to not have to mess around with the whole thing, and I don't want to have to compute a bunch of stuff over here I'm not going to use, and likewise over there. Look at all the work we're saving just by looking at this, what I'm going to call, again, intermediate variables point of view. So that's my pitch. on that one. Okay. Okay, so let's put that into action. Here's a nice example. So we have the following setup. Notice no diagram given. But I do have this f function, and I have this g function, and I've set it up conveniently with variables indicated such that clearly the outputs from f are the inputs to g. Right? In fact, let me highlight that. Whoops. The outs from f are the ins to g. And so you can make your own diagram, pretty immediate consequence. This is the sort of the diagram of the variables, and so f takes the x's to the y's, etc., etc. Quick pause. I am a tremendous believer in drawing these diagrams. The diagram keeps track for you of what variables are playing what role. In particular, you don't have to rely on the algebra once you've got the diagram written. If the question is to find the partial of z2 with respect to x2, I can see right here, there's my intermediate variables. Intermediate variables correspond to paths, and paths correspond to terms. And I can instantly write down my chain rule as applies to that exact question. Everybody on board? Make sure, yeah, come on in. Oh, I thought that was someone else. Well, I guess not. Okay, so, that's a nice little application. Yeah, come on in. Okay, cool. So, there's our chain rule. Now, there's details to be worked out. Y'all are good at this kind of stuff. So let me just point out, for example, how do I compute the partial of z2 with respect to y1? Well, here's z2. Says so right there. How do you take the partial with respect to y1? Y'all know the rules, right? And so there you go. So that part's pretty straightforward. Okay, so now there's a couple of things you need to worry about. This is probably the last thing we're going to get through today is this confusion of variables observation. So it's a real problem. More of a problem than it might look up here. Now, I know y'all are single variable experts. I know y'all know everything there is to know about what's been written there, but just to lay some groundwork for an analogy, I'm going to observe that if I were to give you these two functions, and if I were to then ask you what is the derivative of the composition, y'all know how to do the chain rule. Now, I suppose you could take this formula for f and plug it into there, and you could straight up write the composition. That's not using the chain rule, that's bypassing the chain rule, right? We're here to use the chain rule. So one approach you could take is, and now this is wrong, right? But if you play a little fast and loose, I've already celebrated the pithiness of the phrase, the derivative of a composition is the product of the derivatives. That's, suitably interpreted a true statement. What I have written here is not a suitable interpretation of that, right? This again, playing fast and loose, right? And you clearly get a wrong answer. Now, why did you get a wrong answer with this argument, right? What gave rise to that problem? Well, check it out. These two functions are both written in terms of the same input variable. That's insane. That doesn't make any sense at all. You can't have x be the input to the f function and then also have x be the input for the g function. If you use x as the input for each of f and g, then apparently you're saying that x is what we should call the output from f. And I don't think we should call that x. It's not x, it's x squared. This is a serious confusion of variables problem. Right? Does everybody see the problem there? So, if you're not going to call the output from f x, then you shouldn't call the input to g x either. Right? So, all you got to do, Oh, and now, by the way, you could, of course, you could be sort of like, you could be more careful about how you write down the product of the derivatives, and don't forget this gets evaluated at the output. But I think that's first of all, it's easy to mess that up. It's easy to forget. It's easy to confuse yourself with your own notation. And yes, it does get you to the right answer, but look how much better the following is. So much better and easier. Just don't confuse variables in the first place. Why would we confuse there's no need to confuse variables. These are just dummy variables. They're just placeholders, right? So use them in a way that works for you. And if you're going to, for example, use y to refer to the output from f, well, then, of course, you should have y be the input to g and just rewrite g accordingly. That's the same exact function. That is the same function as we wrote here. Function didn't change at all. Just wrote it in terms of a more appropriate dummy variable. A free country, why not? Make a reasonable choice, right? Make the choice that works for you. And in this case, that's what it is. Now, then, of course, just for good measure, I'm going to give a third name now to the variable that comes out of G. And now look how easy. Look how easy. I can be sloppy with my notation. Derivative of compositions, the product of derivatives. Be as sloppy as you want. What is G prime? Well, boom. What is F prime? Well, no problem. Just write it down. Don't overthink it. Just write it down. And then notice the notation has done the bookkeeping for us. The notation leaves a y, in this case, just the one, in the answer. Then I have to sort of recognize, well, look, the composition should be entirely a function of x. That's what it is. Really shouldn't leave y in my answer. So we better rewrite everything in terms of x. How do I get rid of these y's? Wait, what was y again? Oh yeah, y is the output from f. And that tells you exactly what to plug in. And then, of course, eventually gives you your right answer. Okay, now that's all single variable. And again, hopefully kind of a yawn. Hopefully y'all are very familiar with that, or at least comfortable with that idea. Here's the same thing in multivariable. If two functions come to you with an obvious confusion of variables problem, they're both written in terms of the same inputs, even though we're composing them. It doesn't make any sense at all. Just rewrite one. Whatever you decide to call these outputs from F, those had better be the inputs to your G. Just rewrite G accordingly. And then, again, it does the bookkeeping for you. You can write down the chain rule, be as sloppy as you like. The variables are all going to keep track of what to plug in where. It's all done by the variables. You take the derivatives in the usual way. Make sure to get them in the right order. It's easy to mess that up. Got to make sure to get them in the right order. And then, again, this question comes up eventually of, what is U? And don't forget, U, being the first input to G, is also the first output from F. And that tells us how to plug in accordingly. So anyway, heads up, don't confuse your variables is the punchline. And we'll call it a day right there. Sorry, I went over. We will pick up here tomorrow and head into office hours in just a couple seconds and see some of y'all then. Have a good one.